All right. So regarding what I said about Galois theory previously, um, it is notable that the basic approach that is being taken here, which led to the conclusion that the quintic is unsolvable in general in terms of the coefficients, which it may be. I'm not saying that I have a solution to this bullshit. What I'm saying is, I'm skeptical that that broad of a claim is justified from what has actually been demonstrated with Galois theory. It is notable that what is being attempted is to take the exponents in the polynomial and treat them as if their inverse is roots. Right? That's the whole point of a radical. You're taking the fifth root, the seventh root, the whatever root. Right? That's why, like in the quadratic, you get a square root in there. You also get squares. Squares underneath the square root on the quadratic, and that occurs, I do believe, also in the cubic and the quartic. I don't recall the equations offhand for those, but I think similar things are occurring there. But a problem with this, the problem with this is roots are not the inverse of powers. Roots are powers. Right? They're not inverses of powers. The inverse of powers are logarithms. Right? And I'm not saying that we can just solve this with logarithms, but what I'm saying is the claim that quartics have been proven unsolvable in general, like there's no general solution, hinges on the assumption that raising something to the inverse of what you raised it to in the first place is the opposite of raising it to something. That's just nonsense. Right? 7 to the 2/3, that's not the opposite of 7 to the 3/2. That's just a different power. That's just a different exponent. But the logarithm, base 7 of 2/3, that is legitimately a completely opposite operation. Completely different sort of thing. Completely different beast. But that's not how Galois theory was approached, and that's not how the problem of quintics was approached. Right? And I'm not saying that this is. I even suspect that this is going to yield a resolution to finding a general solution to the quintics. What I'm saying is, it was just approached the wrong way in the first place, and then this grand conclusion was arrived at, and everyone gave up. That's what I'm saying. Right? And that's true. That's what happened. But it wasn't even approached right in the first fucking place. Why are square roots so vitally important? Why are they so magically important? Right? Why are they what makes all of this happen? Right? And maybe you look at like Euler's formula and you're like, well, this is how you get like the multiple roots of things become interchangeable, and that's sort of what's critical to Galois theory, is the interchangeability of those things. But at the same time, our sense of logarithms hasn't actually been developed enough to work out whether there's something analogous to that occurs with logarithms. Maybe there is. There is. There is. Yeah. So there's problems here. There's problems here. And I'm sure this has been to some degree looked at. I just haven't found it. But it should be at the forefront of the discussion of quintics. Right? Like, you shouldn't have to hunt around for this. This should be right there. They should be like, okay, we can't do it with radicals and we can't do it with logarithms, and this is like, see, we tried immediately. Like, that should be your evidence right up front. Right up front, that should be your claim. Like, when we're talking about why it was how it was demonstrated that quintics have no general solution using Galois theory, what should immediately come up is, okay, we looked at radicals, right? Because radicals worked for quadratics, cubics, and quartics. So the question that we were really interested in at the time was whether that will also work for quintics and higher. It turns out it doesn't. Galois theory shows us that. But taking half a second to think about it further, can we use logarithms, which are another, or the proper inverse of exponents, to do this? Because what we're assuming is that radicals, roots, are the inverse of these powers, right? If you have like a 15th degree polynomial, what you want to do is take the 15th root, right? That naively, that seems like what we want to do. So what we're doing is we're treating the 15th root as the inverse of the 15th power. But the inverse operation of these things isn't actually that. The inverse operation is actually logarithms. So what we should do is also look at logarithms. And I'm sure to some degree at this point in history that has been done. But what I'm saying is, like, that should be just right there, up front, with everything else. We're like, yep, and we also looked at logarithms, and it didn't work there either. And now, because, like, tetration builds upon both of those, for sure. Like, there's no more wiggle room in the level of where the exponents live, right? There's no more wiggle room, right? We have our three operations accounted for. We have our base operation, which is logarithms, and our two inverses, which are powers and roots, which are both exponents. Now we've dealt with that level completely, and we can now exclude every other arithmetic operation that's higher than this. Tetration, pentation, whatever. Now you can validly do that. This should be obvious. This should be an obvious thing to look at. Especially when you're going to casually go from saying that quintics were proved generally unsolvable in terms of radicals via Galois theory to the next breath saying, yes, and thus Galois theory proved that quintics are generally unsolvable. There is no general solution. Those are different claims. Those are different claims from each other. And what is actually shown to us doesn't actually warrant both of the claims. It warrants one of them, but not both of them. So this is kind of what I mean when I say, like, this isn't as rigorous as people claim that it is. Math isn't as rigorous as it's claimed to be. There's gaping holes in the logic and reasoning, and there's huge jumps of faith, huge leaps of faith. Like, oh, well, it doesn't work over there, so it doesn't work anywhere. Despite math being keenly aware that that is a completely false way to look at things. It's a completely fallacious way to do business, right? You won't accept, like, if we don't have a proof for Pythagorean theorem, you won't accept it. You'll take it as you'll take things as, what is the word for it? As like a conjecture, right? You'll take things as a conjecture and be like, okay, this seems to work, and we'll run with it, but we need to keep everybody up to date with the fact that this is a conjecture, not a theorem. But then here, It's casually spoken of as if it's been completely proven that there cannot possibly be a general solution to a quintic. Right? Personally, I don't give a shit whether there's a general solution to a quintic or not. I just find it interesting that there's a gaping hole in the reasoning here that apparently nobody sees. Why? Why is everyone blind to this? I don't understand what's happening. Anyway,